Okay, so today we will learn about the sequential logic. So last time we looked at the combinational logic. So in the combinational logic, if the input is changing, then the output is immediately also change depending on the input value. Okay, so wherever the input value is varying, then output will be also changing. Okay, so sequential logic case is kind of a memory. Okay, so using this sequential logic, we are implementing memory or register. Okay, so this component will be implemented using this sequential logic. Okay, so in the sequential logic case, beside with the combinational logic, we have to provide clock. Okay. So when the clock is changing, then the input is changing the internal state of the logics so that the output value is changing. Okay, so that's the difference. So combinational logic case, we don't need clock. But sequential logic case, always we need clock. Okay, so clock is kind of barrier when the output is changing. So that's the most different part. So we will look at this clock first for this sequential logic. Okay. So clock is kind of pulse, like a heartbeat. It's 0 and changing to the 1 and 0 and 1. Okay, so this one period is called clock cycle. So we already learned about that in chapter 1. Okay, so the number of a clock cycle per second is like a clock frequency. Number of how many clock cycles are generated per second. Okay, if we are looking at this clock, there are two parts. One is clock is changing from 0 to 1. Okay, so clock is increasing. So that part, this changing part, the changing part is called lighting edge. It's edge, but lighting means clock value is from 0 to 1. Okay, so that moment is called the lighting edge. The other one, if clock is falling, that is called falling edge. Okay, so in the clock, actually this lighting edge and falling edge, this edge is more important because actually when we are learning about this sequential logic, when the edge point, like a lighting edge or falling edge, at that moment, the input value is actually reflected to the circuit or logic gate. Okay, so then, so there is clock. Then let's look at how we can implement the register using the gate. Okay, if we are looking at the gate, like AND gate, for instance, there is AND. So there are two inputs and one output. Okay, so let's assume that the input value is 0. Okay, and then input is changing to the 1. So it's changing to 1. So initially it was 0, both are 0. And then at some moment, both are changed to 1. Okay. Then actually the output is not immediately changing. We need some time delay, right? So after some time delay, the output value is actually changed. So that is called this delay. But the signal is actually transferred from the input to the output. We need the delay. That delay is called actually propagation delay. propagation delay. Okay. So using this delay, actually, we can implement the sequential logic. So AND gate, for instance, is like this. There is a 1 volt, and A, B, and for instance, this is ground, C. Okay, so this is A and this is B. If A and B are 0, that means it's open, so that the voltage of C is 0 voltage, right? So 0, 1 case also, C is open, so it's 0 voltage. Both are 1, 1, then, so 1, 1 case, it is closed. Okay, so it was 0 voltage, but if it's closed, then the voltage is flowing to C. So it takes some time for this wire. So that we need delay. So that delay is propagation delay, or we are saying that this is gate delay. So each gate has some delay. If we are using complicated delay, complicated gate, then it has more delays. Okay. Okay, so using this delay, how we can make a sequential logic. So first we will look at the SR latch. So we'll learn about the latch first, and then we will learn about the flip-flop. So SR means it's a set, reset. Set, reset, latch. Okay, so it is storing the 1 bit. Okay, so how this looks like is it has 2 inputs, set input and reset input, and then there is a state or output. There is output. Okay, so if both are 0 case, then the output is not changing. Okay, so no change. So previous output is preserved. If set is 1, reset is 1, then output is 0. Set is 1 and reset is 0, then output is 1. And both are 1 case, we are not defined. Okay, so undefined. We will not use this case. So we will use only these 3 case. 0, 0, 0, 1, 1, 0 case. Okay. So the important thing is that input is 0, then in the case, the previous value is just keep going. Okay, so the output is not changing. So how we can make it? So we will implement this one using 2 NOR gate. Okay, so I will draw like this. There is 1 NOR, another NOR, and here there is a reset, and there is set, and this is output Q. And what we are doing is we will make a recursive feedback. So the output of this Q is going inside to the input. And the output of set part is going back to the input to this NOR gate. Okay, so then let's look at what is happening. If this set is 0, 1, and this set is 0, this case. So let's look at what is happening. This is 1, and we don't know this output, right? So we don't know the other one. We have no idea about that. But anyway, what's the output of the cube prime part? So this is 1 or something. is always 1, but there is not. So the output of Q prime is what? So this is 1. Then always this is 1. And there is not, so it is 0. No matter which any kind of input is given, right? If one part is 1, then Q prime will be output 0. Okay, so this is 0. Then what is happening? So this is 0. Okay, is 0. So this is 0, and this is 0. Then what's the output of this Q? 0 or 0 is 0, and there's not. So this is Q is 1. Right? Okay, so let's look at another case. If R is 1, S is 0, then what's that mean? Okay, so we know that input of R part is 1. Okay, and the other input, we don't know. But what's the output of Q part? Yeah, it will be 0, right? Okay, so this is 0, so this is 0, 0, 0. So 0 and 0, that means it is 1. Okay. So at the moment, let's look at what's happening if R is 0. If R is 0, then what is happening? 0. So here, this case, then Q prime is 1, and 0 or 1, not, so still is 0. So nothing is changing. Okay. Okay, so at this moment, let's try to 0, 1, then we know that this is Q is 1, Q prime is 0. At that moment, let's try change it as to the 0. So that input is 1, another input is 0, another input is 1. So the output is 0, and 0, 0 is 1. So nothing is changing. Okay, so whenever the input is 0, then the output is not changing. Okay, so this one is called D-latch. Okay, so using this two NOR, please draw the D-latch in your Logisim simulator. So if you are completing, please type you are complete. So reset is called, this is 1, set is 1, then Q part is 1. And if is 0, then nothing is changed. Okay. If both are 1, that actually we will not define it. Okay. So if both are 1, then it's very dangerous status. So we will not use it. So anyway, so 0 case, nothing is changing. Generally, the sequential logic is more complicated because it has feedback loop. So it's more difficult to analyze it. Anyway, this is SLH. And SLH case, we have to ensure that S and R should not be 1 at once, right? So S is 1 or R is 1, or both R should be both should be 0 value. Okay, so using this SLH, we will make a D-latch. So D means actually is data latch. Okay, so basically it is using the SLH inside of, internally it is using SR. Set and Q value. Okay. Okay, so internally it is using the set reset. Okay, so SLH. Instead of providing the 2 input value, we will use only 1 value data. Okay, so it is only providing the data, 1 bit. And then what we are doing is, so this is sequential logic. So instead of just providing the data, we also providing the clock. Okay, so she is the clock. So when clock is changing, then the input value is reflected, or input value is changing the output. Okay, so input is 0 case, clock is 0 case, nothing is changing. So what we are doing is, we are providing the AND gate here. Okay, and then D is 1, then we are triggered S is 1. If D is 0, then we are triggering reset this 1. Okay, and then what we are doing is, when clock is 1, in that case, only the output is reflected. So clock is connected to this AND. So then if C equals 0, in the case, the output of AND gate is 0. Okay, C equals 0 case, output of AND gate is 0, which means that the Q value is not changing. So clock is a 0 case. The input is not reflected to the circuit. Okay. If C is 1, then Q is depending on the D. If D is 0, then Q is 0. D equal 1, then Q equal 1. So that is latch. D-latch. It has two input, data and clock, and one output. So clock is 0 case, Q is not changing, C equal 1 case, Q is same to the input value. So, okay, that is called D-latch. Okay, so let's go to the logicsim. So we will try to draw this D-latch. Okay. So let's change the name of this schematic instead as SL latch. Okay, so now this is SL latch. Then let's create a new one. Latch. Okay. So using this SL latch, let's make the latch. So there are two input, D and clock. Then we need and large. Okay, so this is D. And C is clock is provided, and you have to make sure that the first one is currently is reset. So the first one should be reset. So the first one should be set. Second one, and out. So first, so currently the default value of this circuit, the SR value, will not be initialized, so it has error. But if we are increasing the clock part, the C part, it is triggered to 1, then the correct value is coming out. So if clock is 1, in the case, the output is depending on the input value. Okay, and clock is 0, then the output is not changing. And next one, then output change, and then changing 1, changing, doesn't change. Okay. Draw this D-latch. So somebody's asking me why we need the D-latch and the latch. Using this latch, we will implementing register. Okay, so we will implement the register using the latch. So we are implementing 1-bit storage using this latch. Okay, so this is latch, but the problem latch is when clock is 1, then the output is just following the input value, which means that if we are changing the input value, then output is also changing. Okay, so we don't like this one. What we want to do is if value is input is stopped, then clock is changing. When the clock is changing, at that moment, this value is reflected. That's what we are trying to do. Okay, so instead of using latch, actually what we are using is we will use flip-flop. Okay, so we will auto flip-flop. The flip-flop. Flip-flop. So flip-flop is actually it's 1-bit register. Okay, so instead of latch case, output is the same to the input when clock is 1. Okay, flip-flop case, the output is input, not every time, when clock is changing. Okay, so for instance, 0 to 1, so lighting edge. Okay, so lighting edge means it's a very short time. Very short time, the input is reflected to the output. After that, even though input is changed, but the output is not reflected at all. Okay, so we are reducing the input change period. That is called flip-flop. So flip-flop is actually implemented using the latch. It's more complicated. So here there is a slide. There is a slide here. This is actually master slave. This is master slave flip-flop. But actually, master slave is not edge triggering, so we will not use this one. What we are using is D flip-flop. Here, this case is like this. So there is a data, and there's clock, but it is edge triggered, so we will use this triangle. So this triangle representing the edge triggering. Edge trigger. Which means that the output is reflected when the clock is changing. Thank you. So this is flip-flop. What is happening? If D is 0, in that case, okay, so let us assume that this is 0 and Q is 1. If clock is just still remaining 0, then nothing is changing. Okay, so D is 0, 1, 0, nothing is changed to the Q. Output is not changing. When this D equals 0 case, if clock is changed to 1, then there's edge, right? When the clock is rising, then the Q part is reflecting the input. So it is changed to 0. After is it changing? So C clock is remaining as a 1, still is 1, but even the D is changed to the other value, output is not changing at all. Okay, so at the trigger case, only the output is reflected when the clock is triggered. So we will not draw the internal feature of this D flip-flop, but let's look at how this is gonna be working in the logic. So open your logic. Let's try create new one. Okay, so there is library. So D flip-flop is here. Okay. So let's provide the input value. The Q D. Another one is for the clock. This is clock. And let's provide the up. Okay. So this is D. This is, and there is another one like reset, enable, clear. So we are just ignoring this part. Okay, so here, if D is changing, nothing is changed to the Q, right? So let's assume that D is 1. If I'm changing the C from 0 to 1, then Q is changing to the 1, right? Latch case, if I'm changing the D, then Q is also changing. Latch case. But flip-flop case, even though I'm changing the D, it doesn't change any value of Q. Okay. Only the Q is changing when C is from 0 to 1. So even this is changed to 1, nothing is changed. So when C is changing from 0 to 1, then Q is reflecting the input value. Okay. So draw this D flip-flop and then check when the Q is changing. So somebody asking that here, this case only rising edge is considered. So if nothing is specified, then lighting is only considered. If you want to make this one is changing when the falling edge, then you have to add NOT gate here. So if you are adding the NOT gate, the input, then this gate is reflecting the input when the clock is falling. Any question for this flip-flop? So flip-flop is most basic structure for the sequential logic. So the flip-flop is most basic one. So even though you don't understand the internal behavior of the D flip-flop, but you have to know about that, what D flip-flop is. Okay. So when the D flip-flop is reflecting the input value. Okay. Okay, so here clock case, what we can do is, let me remove this part. I think I can provide the clock automatically. So if if you are looking at the wire, so then there is clock. Okay, there's clock. So you can interconnect clock to this one. Okay, so definitely you can change the clock by pressing this one. Okay, so this is 0 and this is 1, this is 0. Okay. And also automatically you can try triggering this clock by using the menu. So if you are going to the simulator, there is a enabled. So let me share. You are going to the menu. There is a enabled, tick enabled. Then the clock is automatically changing. You can see the clock is animated. Okay, so if you're doing the tick enabled, and okay, so let me share. So let's look at the screen. So if you are going to the menu, there is a simulate, right? So there is in the simulator menu, there is a tick enabled. If you are pressing this tick enabled, then automatically clock is triggered. So if you turn on, turn off, then it's stopped. Or you can turn on. And you can adjust the clock frequency here, this case 1 Hertz, which means that every second it is triggered. So if you're using the 4 Hertz, then it's much fast. Really fast. Okay. So you can adjust clock frequency. Okay. And also you can go to the logging. Then so let's add this add input and output. Okay, so you can add some logging part. And then if you're changing the input, okay, so you can change it. And logging part, you can add a clock. Let me stop the simulation. Let's go to the logging. you can add more signal. So add this clock. Okay. And then if you are triggering, then you can see that clock is changing and input also change. Okay. So you can record any logging using this log message, log window. Okay. So can you try to use this log also? So add this clock and then start to the tick. After that, you're adding logging to see that whether the output is correctly coming out. Okay, so any question about this flip-flop? No question? Okay, so then our goal is actually to construct register using this flip-flop. Okay, so to make a register is the goal. So let's try to make a register. So in MIPS, there are 32 registers. Each register is 32-bit register. So first, we will implement 1-bit register. 1-bit register. Okay. So register is basically using the flip-flop. What we need for this register is, it's like this. So there is a register. There's input. And there is the output. That's the basic. And also there is clock. So input is only reflected when the clock is changing, clock is writing it. And also register case, what we need is, sometimes we are writing the data to the register, but in some cases we are not writing. So we have to give some another signal, which is load signal. So load is 1, a 0 case, then output is not changing. It's not changing. Load is 1, then output is changing from input when clock is rising. Okay. So that's the register. So when you are looking at the register is changing when you are trying to update it, right? So in some cases, we just read data from the register. For instance, add instruction, $1, $2, $3. So these two, $2, $3 is only read register, and $1 is writable, right? So $1 register case, we have to give load signal. For the $2 and $3 case, there is no load signal at all. Load signal is 0. Okay. So that's the difference. So register case, we need load signal, additional load signal. That's the only difference. So then how we can implement using D flip-flop. So there is a D, and there is a clock, and there is output. So there are two ways. One is, it's like this. If load is 0 case, then we are not providing the input value. So let's say this is input. Input is selected when load is 1. Load is 1, then the input is coming out. If load is 0, then the output of the gate is chosen. So this is a box. Right? So load is 0 case. The output is provided to the input. So output value is not changing. Load is 1, then input is provided. So the clock is changing, then the output is updated. Or you can implement using some other approach. So it's totally depending on your decision. Like you are just connecting the input to the flip-flop, and you're adding AND gate here. Okay, so load is 0 case, the clock is not changing. If load is 1, then clock is, when the clock is changing, the clock is reflected the flip-flop, the flip-flop. Okay. So can you draw these two things in the logic sim? Mux is multiplexer. Mux is here. In the flexor, there is a multiplexer here. Mux. So it's a selection of the input value. So using D flip-flop, I think there is a D flip-flop in memory. There's a D flip-flop. Using Mux. Mux is selection of the input. Okay. And if load is 0, then output is chosen. Otherwise, input is reflected. So one of them is, I don't know which is the selection bit. One of them is selection. Okay, so first one is selection bit. So here, this case, input, this is the output, this is load. So if the load is 0 case, even though clock is changing, not changing, but if I'm changing the load, let me throw the clock. One, in the case if clock is changing, okay, so I'll reflect it. And if load is 0 case, it's not changing. Or simply you're writing using AND gate. Load. Clock. And then in this case also, even though clock is changing, listen, this one, then reflect that. And clock is changing. Okay, so you are completing it. Actually, there is a register here in the memory. There is a register, so it is already implemented. Okay, so if you're pressing it, you can adjust the input data bit width. So currently is 8-bit. Then trigger is writing edge. You can change it, following it to writing edge, or depending on the high level, low level. High level means when the clock is 1, then the output is changing. Lower 0, then it's changing. So let's try to use writing edge. And let's try to provide input value. If you're connecting to the input, then the bit is not matched. So you have to increase data bits to the output is also to increase. Okay. And then enable clock clear. So enable is kind of load signal. Okay. So this is clock. So default values will be 1 in the enable clock. Let's change. So when clock is changing, it is updating. Okay. If you are adding the load, so input is 0 case, then even though you're changing it, output is not changing now. Now this one, in the case, the output is changed. So you can make a 32-bit register. Let's try to 32-bit. This one is also 32-bit, and this is also. Okay, can you draw this 32-bit register? Okay, so now you are understanding how to implement this 32-bit register. Actually, we know that how to implement 1-bit register, right? So combining this 1-bit register, then we can make a 2-bit register, and combine this 2-bit register, 4-bit, 8-bit, 16, and 32-bit register. So 32-bit register is actually containing 32 1-bit register inside. Okay. So next time, what we will learn is that using this 1-bit register, we are making register file. Register file means that in MIPS case, there are 32 registers, right? There are 32 registers. So how we are making these 32 registers, and in the real instruction case, real instruction is reading 2 register values, right? 2 register values, and then from this 2 register value, it is computing something, and the result is written to the register again. Okay, so we will design these 32 registers, which is called register file. Okay, so we will learn about that next time. Okay, any question? No question? Okay. So then see you on Wednesday. No, Wednesday is a holiday, right? Wednesday is, I think it is Children's Day. So let's see next week, next Monday. Bye.